Okay. Hello, everyone. So my name is Uwe Lewinsky. I work for Codeplay in Edinburgh, and I'm doing research on targeting SYCL to new types of hardware and platforms. I'm involved in this project that Michael mentioned early on, Cyclops and IROS, so they both target RISC-V. They both advance the one API ecosystem. There will a lot of performance optimizations to do with cloud applications, and there will also be improvements to Cyclomatic, so which is a tool to translate CUDA into SYCL. So I'm also doing, so I've done a lot of compiler work. I've been involved in, I've written a lot of patches for Compute CVP, which is Codeplay SYCL implementation. And but I'm also interested in bringing SYCL to new applications, and this is why I'm here to talk about the acceleration of Simulink and Matlab with SYCL. So company slides, I'm sure you probably have seen this. So small company, it's an SME, 90 staff, subsidiary of Intel now, and so main focus is one API, but we have our own products, Compute CPU, SYCL implementation, and Compute Auto, which is a framework to produce runtimes, and these are our customers. So why would anyone want to accelerate Simulink and Matlab with SYCL? Because many applications, automotive, avionics, defense, and other areas are written entirely in Simulink and Matlab. So some people even say that Simulink and Matlab are the de facto standard in embedded programming. So companies typically have very large code bases, and I mean the developer communities, SYCL and Matlab Simulink communities are, I would say, fairly disjoint. So we don't really know as a SYCL community what's going on unless you really talk to these companies. But they have large code bases, and the expertise that the engineers have is mainly in these tool chains and the toolboxes that come with these tool chains. There's a lot of and the support they get through these toolboxes. It's a lot of advanced computation, but also verification toolboxes. So, and yeah, one other important target is safety critical. So by accelerating Simulink Matlab, we can take advantage of open source tool chains and acceleration ecosystems. So we can accelerate the application with more types of platforms that are not supported natively by Matlab, and different libraries can be used at backends like Eigen or Armadillo, and then it's the ability to apply different verification tools. So that's not just the stuff that you get with Matlab, but also things that you can use on the C++ level. Matlab Simulink are widely taught at universities, and many projects are based on similar technologies and open source technologies like Octave, Console, Skylab. So, but we had a more direct reason to get involved in this because we took part in this project, which is an innovative, it's called WISER, and that the aim of this project was to build novel high performance batteries, hybrid batteries for electric vehicles. So it was led by Williams Advanced Engineering, so the people who do the Formula 1 cars. And they built a new hybrid battery, and such a battery always comes with a battery management system. And the purpose of the battery system really is to provide battery safety, so that the battery can't be used in a way that destroys the battery or degrades the lifespan prematurely. For battery monitoring, so you can see the state of health and state of charge of the battery, but also for optimization. So if you have a hybrid battery, you want to use the battery most efficiently for the scenario that you. So if you need more power, you probably want to use one type of battery. If you want a more steady supply of energy, then you want to use a different battery. So the battery management has managed this. So and here on the left-hand side, so this is the is a photo from Imperial College website. So Imperial College was a partner. They provided all the research on the battery chemistry side, and they fed that into, so and they then built together with Williams the battery management system, and it ran on this platform, on this MPSOC platform, directly on the battery. So and this is some ARM64, some ARM A53 cores. There's some FPGA on it. There's a real-time processor on it, and there's an ARM GPU on it. So there's 4 platforms essentially that could be used for acceleration, but we only targeted 2. So this is really the flow, how it works. So the models come in, developed by Williams and Imperial. They were fed through the toolchain called Simulink coder, Matlab Simulink coder, and that generates C code, mostly C code, which is then integrated into the battery management software and into the battery management system. And we replace this with our tool flow, which is in the green box. And so we have our own little coder which translates SYCL it translates the Simulink and Matlab model into C++ with that uses an API that calls into SYCL. So and by targeting SYCL, it enabled us to target the CPU and the FPGA on the platform. So for the math computation, we use the Eigen library. Yeah, so quick overview of what Matlab is. So it's really, I think, MathWorks is described as a block diagram environment to build complex dynamic systems, and it comes with a multi-purpose programming language, dynamically typed programming language. Simulink models are really blocks of graphs that can be very simple, but can also be extremely complex up to the point where you have lots of blocks in the system, and each block can contain function calls and reference whole Matlab libraries. There's different blocks for data storage, state flow, which is a concept, which is another type of block in Simulink, control for math operations. So there's a list of frequently used blocks in Matlab. And so essentially each block has inputs and outputs and block parameters. And yeah, on the right hand side there's a photo of there's an image of a Simulink model taken from the MathWorks website. So just to see how it looks in a graphical environment. But the Matlab and Simulink interactions are that that blocks can have Matlab code attached to them, full functions, but also just expressions as block parameters to configure the block in certain ways. But there's also, and Matlab itself as a program language, it's used to configure the workspace and is also called to query the Simulink model. So typical Matlab Simulink file contains the Matlab solution files, the SLX files or MDL files. So this SLX files essentially XML files. Then it can also contain Matlab files. So they can be workspace setup files, but also free functions that can be called from other functions or from the Simulink model. There can be embedded functions and blocks and anonymous functions. And then you have Matlab data files with a proprietary, which is just a binary format, and that contains workspace data and simulation data, all those kind of things. So now our approach really was to convert, from a technical point of view, it's really converting the Simulink, all these files, putting them together and converting them into C++ that can be accelerated with SYCL. So we want to take advantage of open source libraries, open source to do all this. So and we got a lot of help on the data format front, but also on the math operations for Eigen. There should be no dependencies on the Matlab installation, and it should be non-disruptive. So it should really enable the engineers to continue to develop the Simulink, be productive in their way of coding as much as you can, so without having to look into technical details. I think this is similar to what was mentioned on the panel earlier, that focus on the problem and not the implementation. And then, so there should be an option. It should be to run the entire model step or individual blocks as SYCL kernels. And the other approach was we only implemented stuff that we needed. So it's pretty much an Occam's razor approach. There's some other related Matlab projects that also Intel, for instance, Intel provide this integration where you can call the data analytics library from a Matlab from a Simulink model, and they use this through this MEX interface. There's CocoSim, which is a completely open source verification tool, but it requires a Matlab installation. And then there's some other open source tool which already converts Matlab files, but it didn't really. It seems to be very limited in, and we couldn't really use it for the functions that were used in the project. The challenges of the integration. Integrating the output of various different tools and different type formats. Then the support of different block types. So there's different types of blocks, or I mentioned submodels, references to models, subsystems, and there's different notions of subsystems in Matlab, which I probably shouldn't go into, but they're all connected by ports. And so the challenge is really to put all this together and generate a model step which evaluates the entire model. And that means we need to determine the execution order, and so this requires some kind of block schedule to execute the blocks in the most efficient order. So and then outputting the code as C++ code and integrating it with the backend, which is Eigen. Then, of course, targeting SYCL is a big challenge, and providing flexibility and configurability for the user to try out as many integrations, or as many options to compile the code differently to get to tune performance. The open source projects that are used in this project were the Concord library, so it's an open source library to read in the Matlab files and build the model graph. And the Matlab files are read by this Heavy Roberts MFL library. So this is some small example how we translated the code. So we essentially translated the model on the right-hand side. So this is a model that has two similar or almost identical subgraphs. So we fed this through Tor, and on the left-hand side you see the output. So it starts really with the inclusion of the API header, followed by the model inputs and outputs, and then followed by the model step function, which does the evaluation. And that function just goes through all the blocks in the order they are ready, in the order they have their values supplied to them. And executes them. And finally, the results need to be written back to the outputs. So that really concludes it. And so this is all that there's to it. But this is a very simple model, and so it only has 25 blocks. So and industry grade models have thousands of blocks. So one other advantage of the thing is you can have a look at the block parameters. So this allows some kind of introspection that isn't really possible with Matlab, because if you want to introspect all the parameters, you would have to go through all the blocks and click through all the different options, and that might be quite time-consuming and tedious. So it's much better to output all the block parameters as comments in source code, and that just allows you to search through certain things and verify and look for certain parameters that you want to evaluate or tweak. So the Eigen integration is really yeah, it's really in a way behind this API. So we, for instance, from the previous example, you see the subtract function, and the subtract function really takes implements all sorts of overloads, and if the parameters, if the arguments of the function are eigentypes or other types, then the right overload is selected and the right operation is called. And then we have this matrix data type, and which is also used for many of the API functions, which can embed eigen as the base type, but it can also import other backends. So this is the SYCL integration. So what we did is we targeted a system called for each. So for each systems are essentially systems that are executed by a for each loop. And this is, so they're just declared by just putting this for each block inside a subsystem, and that contains parameters about dimensions of the block, and that's all there is. So, and this yeah, essentially turns the subsystem into a vector or an array. So, and it needs to duplicate all the state that the system may have, and then we can just apply SYCL power 4 to evaluate this. So there's some other little roadblocks, and when you want to convert Matlab to Simulink and Matlab and Simulink to C++, and there's persistent global variables which can be in Matlab functions, and they are essentially local statics, so they need to be hoisted out of the function. So here we have the SYCL integration shown by an example. So it just creates a struct with a function call operator that evaluates the entire system, and so this and then it just creates a static array of the requested dimension for this. And the way it's processed is it calls a for each function, which should probably now which will in the future probably align with the C++ for each, but right now it's our own for each. So it takes the kernel name, it takes the SYCL state. So SYCL state contains the queue, but in some cases also buffers. Then the functor array and the arguments. And the output, because it creates now a vector of systems, the outputs now need to be concatenated, and this is what the process molFE function does. So then afterwards, we use the get element, which can probably be a std get function to extract the value from the return value to process them on for the following blocks. So this code can be built with a normal C++ compiler. So we really wanted to make it so very, very simple, so that people who don't have experience with C++ tool chains, so they can use them very easily, integrate very easily. And if you want to compile it for SYCL, you just use the one API compiler and just pass the SYCL option and use SYCL. So this is important to enable the SYCL acceleration and mechanism behind the scenes. Which are also, this slide also is related to this. So we want to be able to, so when we output a model that contains a lot of for each systems, for each system, it creates a kernel name and it lists them all in at the bottom. And the user can then decide by defining a macro whether this kernel runs as a SYCL kernel or whether it runs as normal CPU functions. So that really enables some kind of auto tuning that you can do to see which combination of kernels give the best performance. So, and of course, there's a lot of limitations of the current thing, because it's, as I mentioned, it's an Occam's razor. implementation. So there's only a subset of Simulink blocks are supported, and of these supported blocks, only a subset of block parameters are supported. Then there's file format problems. So the Simulink files have to be in Matlab format 2020 or older. But this is sometimes, or this, most problems can be downgraded to this more recent project can be downgraded to this format. But then there's also the data file format. So data file format have to in version 5, and Matlab has moved on quite a bit from them, but you can still save it back with open source software like Octave, which support that format. So there's no Google Simulink commands supported in Matlab code, but yeah, for the battery management, we didn't need this because they didn't use that. And so there's backend limitations. Not all of Matlab operations can be directly matched to Eigen. So there's a lot of things that we used in the unsupported modules and Eigen modules, and there's also things that we needed to build on top of that. Currently it's using synchronous execution, which means this parallel for each that I showed you is really needs to wait until everything is finished, when it should really be better to launch all the different iterations asynchronously. And there's task parallelization opportunities that are not exploited yet. So if there's different strands of or different subgraphs of the block that can be evaluated in parallel. So they're currently executed in sequence, and so this can be parallelized. So this takes me to future ideas. So targeting new and updated use case. So we're still working on battery management system models. So there's some open source project currently that I'm looking at, and I really like to yeah, output really publish the results of the conversion and show how this works on an industry grade project. Then there's the auto-tuner I mentioned, so to see which kernel runs where and with what parameters. Then there's the asynchronous execution of SYCL kernels. Then we can also integrate the Eigen SYCL backend, which we currently haven't do. So this is really to evaluate the expression trees and use the SYCL support for this evaluation that's currently in the Eigen SYCL backend. Then yeah, generate different block schedules for performance. So just changing the order of the evaluation. So this maybe improves memory accesses, makes access contiguous, or improves performance in other ways. Then the task parallelization I mentioned, then improve buffer creation. So right now the buffer creation is fairly naive. So most of the buffers are created at the time when the subsystem is evaluated, so it could be really done earlier. Then we want to target, then we could support DSM, which we currently don't. Then other block types, supporting other block types, then target the whole thing to safety critical. So this SYCL for safety critical. Potentially open source it and publish results on performance numbers on a real use case. Yes, unfortunately, I can't show performance numbers because we couldn't find an open source Simulink model that uses for each blocks, and but we're trying to find a solution for that so that we can show how this works. Yeah, so with that, there's a conclusion. So presented an open source based tool flow to translate Simulink Matlab C++, no dependency on Matlab tools, accelerates by SYCL, generates a static model structure. So this is really important for deterministic model evaluation, at least for C++ without SYCL, because there's no in C++, on the C++ version, there's no memory allocation going on. Whereas in SYCL, you have enqueuing tasks and things, so they might, in the current version of SYCL, allocate memory, but safety critical version, it may not. So then, yes, we did it on an industrial use case. So it's a working industrial use case, and we got some performance improvement with a very naive implementation. Unfortunately, not on ARM, but on Intel. But it's really, we need to find an open source model to really be able to publish the numbers. So it had to be really non-disruptive, because we want, or the Simulink engineers didn't have any experience with SYCL and didn't have time to look into this and have to concentrate on their Simulink work. And the generated C++ code provides different options to evaluate the entire model in different ways, just as either the entire model as model steps or individual blocks. And so you could selectively enable SYCL per block. Acknowledgement. So this work was partly supported by IWOCL Newsletter. So this project has kickstarted a lot of interesting technologies at Coplay, including the CPU acceleration in SYCL and the target support for FPGAs. There's already disclaimers, which I need to show you, and well, that's some through.
Any questions for our speaker? I guess I had a question. You said that you're preparing a paper with performance results. Are you able to spoil something? Did you see a performance improvement? You said that the hardware had all different sorts of things on it. So
yeah, no, we need to. The thing is, we need to find an open source use case to do it, and we're still in the process of compiling that use case and making it look, or making it very similar to, or the scenario very similar to the type of code that was used in this particular model.
Yeah.
So,
okay. Yeah. And how about the memory? Like, how does the memory systems in SYCL, the USM or buffers and allocators, how does that all play into the data that you get from Simulink and Matlab and Eigen? How do you map the memory? Who controls the memory?
No, so the buffers are created by this function. I should have shown a slide on this. So essentially by this parallel for function. So when it takes the input functor, it just creates a buffer for this particular functor, and then just passes the accesses to this buffer on, and that's how the SYCL kernels can all process the data.
Yeah.
So
yeah, so for each block, it creates a separate memory allocation, processes it, and then hands it back.
Yeah, but the idea is really to encapsulate all this allocation, do this ahead of model evaluation in the state struct that is passed to the model step, and that contains the queue where we want to or the queues that we want to submit the kernels to, and the buffers that are used by the kernels, so that we can do it ahead of time. And because the kernel the model step is really called in the loop, so we don't want to create buffers in the loop. But,
and is there any other plans to support other parts of Matlab, not just within these particular libraries and files? You support for each. Is there other constructs in Matlab that you think could be?
Yes, I definitely want to exploit this task parallelism. So then different block orders. There's probably other. Then there's some parallelism exposed by Matlab functions themselves. So yeah, but it's probably all done on a per, if it's really needed, basis. So I don't think we want to solve everything. We just want to solve the use case that we're working on.
Okay, great. Thanks. Christian?
Yeah, so Simulink I know that that's the automotive engineers loved using that because it seems to be an auto code generator. What is it about? I'm trying to understand how is it that they continue to work while you're doing the SYCL part? Because are they still just automatically generating the Simulink, or is that?
No, the important thing is the developers, they are Simulink developers, and they wouldn't use SYCL.
Okay.
So they wouldn't change, they have legacy code base, they will never
I see.
change
They're
it.
never
So-
going to use SYCL.
so-
they just use Simulink, and you're
Yeah.
intercepting the Simulink.
So it's actually, so SYCL is really a backend to this technology. It's in
Okay.
the same way that SYCL is a backend to the Onyx runtime, you know, where
Okay.
people are still able to can develop their models in
Okay.
TensorFlow or whatever, and then just, but benefit from the SYCL acceleration at the backend.
And the synchronous versus the asynchronous choice. So you're doing synchronously now,
Yeah,
and you think that if you implement an asynchronous capability, is that for asynchronous dispatch or asynchronous functions?
Yeah,
for,
so this-
for each kernels?
yeah, so it's asynchronous dispatch, so
Okay.
we can enqueue the kernels asynchronously, and also that so that you can do other stuff while
While it's
the
waiting.
kernel is
So you
still
must have
being enqueued.
hundreds and thousands of these running then.
Yep.
That's
Yep.
usually where you buy a lot if
Yep.
you have for asynchrony. Yeah.
Yeah.
Okay.
So, yeah.
Okay.
But even within with the synchronous approach, we got some promising results. But that may be that the model was badly designed. But I don't.
Yeah. No.
But yeah.
Never know. Okay. Thanks.
Okay, with that, if there's no more questions, we'll thank our speaker. Thank you.